Ladies and gentlemen, we have detected gravitational waves. We did it. I am so pleased to be able to tell you that. So these gravitational waves were produced by two colliding black holes that came together, merged to form a single black hole about 1.3 billion years ago. They were detected by LIGO, the Laser Interferometer Gravitational Wave Observatory. LIGO is the most precise measuring device ever built. Let me start with what we saw. So on September 14th, 2015, the two LIGO observatories in Hanford, Washington and Livingston, Louisiana recorded a signal nearly at the same time, nearly simultaneously, and the signal had a very specific characteristic. The characteristic of, as time went forward, the frequency went up. And what was amazing about this signal is that it's exactly what you would expect, what Einstein's theory of general relativity would predict for two big massive objects like black holes inspiraling and merging together. Now, it took us months of careful checking, rechecking, analysis, looking at every piece of data to make sure that what we saw was not something that wasn't a gravitational wave, but in fact it was a gravitational wave. And we've convinced ourselves that's the case, and we're here to announce that today. But I do want to say something else. This is not just about the detection of gravitational waves. That's the story today. But what's really exciting is what comes next. Right, it's 400 years ago, Galileo turned a telescope to the sky and opened the era of modern observational astronomy. I think we're doing something equally important here today. I think we're opening a window on the universe, the window of gravitational wave astronomy. So I'm going to show you two videos that are going to sort of tell you what we discovered. So the first video is the two black holes. So what you're looking at on the screen here are two black holes. Each of them are about 30 solar mass, have about 30 times the mass of the sun. All right, and you're looking, the black holes are the black things in the middle, and you're looking at the stars behind them. By the way, this is not a Hollywood production that I'm going to show you. It is actually a real computer simulation solving Einstein's equations for these merging black holes. So this is really what it would look like if you were in a spaceship close up. And I will also point out that the movie I'm showing is vastly slowed down relative to what happened here. So let me start it. All right, you can see that as the black holes spin around each other, all right, the stars behind them are warped, and that's because the strong gravitational fields bend the light that comes around. But what I want you to pay attention to in this video is the fact that as they orbit, the black holes are getting closer and closer to one another. The orbit is speeding up, and eventually they're going to merge. The event horizons are going to join, boom. They produce one big black hole, which relaxes, and you see a little bit of vibration there, and it becomes two smaller black holes die, one bigger black hole is born. Now, what's really amazing about this is the first time that this kind of a system has ever been seen, a binary black hole merger. And it's proof that binary black holes exist in the universe. So I want to put this in perspective for you because I think it's very important, all right, to give a sense of what really happened here. So each of these black holes are about 150 kilometers in diameter, a little bit bigger than that. Take something that's 150 kilometers in diameter, so that's about a little bit bigger, maybe a lot bigger than the metropolitan Washington, D.C. area. Pack 30 times the mass of the sun in that. Accelerate it to about half the speed of light. Now take another thing, 30 times the mass of the sun, accelerate at half the speed of light, and collide them together. That's what we saw here. It's mind-boggling. All right, now, let me talk about the gravitational waves. You didn't see any gravitational waves there. What you saw was actually the black holes. Now let me look at this from the gravitational wave perspective. So you're going to see, again, a computer simulation. This is a real simulation using Einstein's equations. You see the two black holes. And the green that you see are the gravitational waves that are produced as the black holes orbit around one another. Their orbit decays and they merge together. All right. So they're spinning around. You see they're getting closer and closer together. As they get closer and closer together, more gravitational waves, they merge, and there's this burst of gravitational waves that travels for 1.3 billion years. It passes through everything. It goes right through matter, right through stars, and it eventually gets to the Earth. All right, and when it gets to the Earth, the gravitational wave passes, and what it's going to do is stretch and compress space as these waves pass. And you'll see that the Earth is jiggling like jello. I don't want people to be scared here. The Earth doesn't really do this. This effect is greatly, greatly exaggerated, but it gives you the effect. And then we zoom in, and how we detect these are using the interferometer that's in LIGO. And Ray Weiss is going to tell you more about the interferometer. I just want to say one thing, that the effect that we're trying to measure from these violent, these big black holes colliding each other at half the speed of light, all right, is so tiny that it takes something like LIGO to measure it. We are trying to measure things basically at 1/1000th the diameter of a proton. That's the size of the signal that you see on Earth from those events that take place 1.3 billion years away. All right. Let me put that in perspective, because I think those kinds of numbers are hard to get your head around. All right. If we were trying to measure the distance between the sun and the nearest star, which is about 3¼ light years away, LIGO is capable of measuring that, if it could do that, to a level of about the width of a human hair. So the width of a human hair over 3¼ light years. That's remarkable precision. Right? Now what LIGO does is it actually takes these vibrations in space-time, these ripples in space-time, and it records them on a photodetector, and you can actually hear them. So what LIGO has done, it's the first time the universe has spoken to us through gravitational waves. And this is remarkable. Up till now we've been deaf to gravitational waves, but today we're able to hear them. That's just amazing to me. I think this is big, again, because what's going to come now is we're going to be able to hear more of these things. And no doubt we'll hear things that we expected to hear, like binary black holes or perhaps binary neutron stars colliding. But we will also hear things that we never expected. And as we open a new window in astronomy, we may see things that we never saw before. So let me conclude by thanking the National Science Foundation. For 40 years, since the NSF started funding Caltech and MIT to do pilot experiments for LIGO, and then in 1992, the NSF went ahead and funded the LIGO project, right? And they took a big risk, all right? This was bold. The science was solid, but we didn't know how many events we would see. The technology was nowhere near developed. This was truly, I think, a scientific moonshot. I really believe that. And we did it. We landed on the moon. So I really want to thank Dr. Cordova and NSF, and also U.S. Congress, the taxpayers who've supported this research, because it's really, really gotten to the point now where it's going to take off.